All right, in this video we're going to apply the projection matrices to problems of fitting straight lines or parabola through some noisy data sets. And so I've generated some synthetic data over here. I have two files. The top one is called data1.csv and the bottom one data2. And what we have is the first column is a set of times and then a set of measurements. So we can assume, for example, that these are wind speeds in meters per second if we wanted. Same thing for the next one. All right, so let's load these data up and see what they look like. So load data1.csv, and then T would be so data1 is a 2 by 10 or a 10 by 2 matrix, and so the time variable will be the first column, 1, and the speed, let's call it D, the data, is the second one. And now let's make a plot of it. It's always good practice to plot the data. And let me stretch it out. So maybe I should connect the points with the line so it's easier to see. All right, so this is the first data set, and if we look at it, it sure looks like there is some kind of trend, right? Things are increasing. There's some variation. It's not a perfect fit, but there is some trend in there, and we want to try to estimate it. Also notice that the x-axis, the y-axis, I mean, starts at 2 to 6.5, so it doesn't start at 0. So it seems like there's also a mean offset to the time series, which we should try to estimate also. Okay, so how are we going to do this? So I have two data, D and T. So far, I have T, which is a vector of numbers from 1.0 all the way up to 10.0. And then I have the data vector, D, and this one has the numbers 2.12, 2.65, all the way down to 5.53. All right, so our model is going to be, I'm going to say F. I'll put in the vector F, and it will correspond to values F1, F2, all the way up to F10. Now, we don't know what the fitted model will be, but we want it to be of the following form. So F1 should be equal to some mean value and a trend. So the trend would be something like A times T1 plus B. And the second one, F2, would be A times T2 plus B. And we can keep going all the way down to F10 is equal to A times T10 plus B. And we want to somehow choose A and B in such a way that this is a good model for the data we have. And so to explain how this is all going to work, what I'm going to do is write this expression here in a vector form. So this is the same thing as F. The vector F, this one, is equal to A times the vector T plus B. And B, we can think of it as number multiplying a column of ones. So 1 times B. So what is this vector 1? So 1, I'll put it over here. It's a vector. It's 1, 1, all the way up to 1. And this is a 10 by 1 vector. 10 rows. And I can rewrite this expression in matrix form. So that I have F is equal to, and remember T is a column and 1 is a column. Both are 10 by 1, so I can put them one beside the other, times a vector A and B. So this is the form of our model F. Now the model has only 2 degrees of freedom, just 2. And so you could think of it as being lying in the plane spanned by the vector t and the vector 1. So if we go back to the picture we had last time, I have this plane that's living in a 10-dimensional space, right? So the data t has 10 components and 1 has 10 components. So we'll have a vector something like this, t, and this is a 10 by 1 column vector, and then a second vector, this one vector. And the data, f, no, not f, d, it has 10 components, so of course it will not lie in the plane because it isn't, if we look at the data, it's not a perfect straight line. So this space here, it really means a 10-dimensional space. So the data is going to be out here somewhere. There's going to be a component of the data which does not lie in the plane. And so what we want to do is to find the fit of the model. We're going to project the data onto a plane where the only thing we have are perfect straight lines, right? So they're going to be just models of this form. So this plane is the space of all possible linear fits through our 10 data points. Nothing else exists. And so the time series is not a perfect straight line, so there'll be a component off the plane, and that's what we're going to call E, the error. E. And this vector here is the fitted model F. So we can use the same formula that we derived in the previous lecture to find out what A and B is, or what is this model F. So the model, so let's give these matrices some names. So this one, I'll call it M. This one here, which is the parameters, I'll call it beta. And now we have what we need. So we have F is equal to M times beta. And we want to make E perpendicular to the plane. And that means we do the projection. So F is equal to M times M primed M inverse M prime data. So this is our best fit beta. And it will turn out that this beta is the least squares fit. And I'll explain why that is in a bit, but you could think of it this way. The beta fit makes this E perpendicular to the plane. If we were to make the residual, the difference between F and D, to be not perpendicular, then it would be coming out at some angle like this, right? And this line, the length of this vector from here, from this point to this point, is clearly longer than the one that's perpendicular. And so that way it means that if we take the length squared of E and compare it to the length squared of this residual, this one is smaller than this one. So this is, in that sense, what we're finding is what's called a least squares fit of the data D to the model consisting of perfect straight lines. So we can go to the computer and compute what beta is and what F is. So let's do that. So I'll move the data over here, the plotted data. Let me give it an x-axis. X label is T, and Y label is D. Okay, so now we're going to compute beta. So the first thing we need is to compute M. So construct M. And M, the first column of N is T. And the second one is a column of ones. We can do it this way. Ones of length of T, comma 1. All right, so this will generate a vector of ones. But this is not a nice way to do it. So a better way to do it is in the following. I like this better. T hat 0. So we have t to the power 1 as the first column and t to the power 0 in the second column. So anything raised to the 0th power gives us 1s. So we'll have the matrix we want. So this is the M matrix, and this matrix is often called the design matrix. Design matrix. Okay, so we can compute beta. So beta is equal to m prime star m backslash m prime star d. And boom, that's all there is to it. We have our two parameters, so that was very easy. So so beta, the estimate for beta, it turns out for this problem we get beta, which is equal to a and b. We find 0.3673, 0.3673, and for b we get 2.0560. So this is a. So a, remember, is the slope of the trend, so it's a positive number. And sure enough, if we look at the data, it's an increasing trend. And b, the value is 2.0, and b corresponds to the value of d, or the height, at time t0, and it's very close to 2, so that seems reasonable also. Maybe we should try to plot it on top of the curve. So we do hold on, and f, remember f is equal to m times beta. So I've generated f, and now we'll plot it. So plot t, f, and this one I will plot in red, so we can compare the two. And this looks like a reasonably good fit, right? The residuals are on either side of the line, and there you have it. So that was fitting a straight line through data using projection. Let's do the second data set. So if I clear everything, clear all, CLF, let's load data2.csv, and let's plot it again. T data. Oh, I have to create. Wait, data 2. Yeah, I have to extract T. Data 2 and D. Data 2. All right. So let's plot it. Right, so in this time, this data set also has a trend. It seems to be a decreasing trend, but more than that, it looks like there might be some curvature to it. But let's start off by just fitting a straight line through this data, since we know how to do it. So m is equal to this. This is the design matrix. We're going to fit a straight line. And beta. So last time I did this formula, I could do the same thing in MATLAB, an even easier way. So if I just do beta is equal to m backslash d. M, remember, the matrix M is not a square matrix, so it doesn't have an inverse. So when you do beta equals to m backslash d, what MATLAB does is it solves the least squares problem. So it solves this equation, the one I had written out explicitly. So we get the same answer in either case. All right, so let me write this down. So for the second data set, so let me copy it over here. Beta is equal to a and b, and the values we got were minus 1.8080. That's the slope, and 5.726 is the intercept, the value at t equals 0. Okay, so it doesn't look so good for the intercept, but let's plot the resulting fit. So f is equal to m star beta, and we can plot In red, we want something. Yes, this one. Plot the fit. Oh, I didn't do. Did I do hold on? Hold on. Plot. All right, so that's not too bad a fit, but it does look like there's some kind of curvature. If you look, the first value is below the line, the last one is below the line, but the middle ones, there's 1, 2, 3, 4, 5, 6. 6 points are all above the line. Only one is below the line in the middle. So maybe it's a straight line. It could just be, but we can also see if a quadratic model, one that includes some curvature, might be a better model. And so we're going to do the same thing, but this time we'll include an extra column to our model. So if I create my design matrix M, now I will add a t squared. So notice how the first column is t to the power 2, the middle one is t to the power 1, and the last one is t to the power 0. So I could show you what it looks like. This would be the design matrix, or the model. Each column is a vector that spans what's called a hyperplane, or a subspace of 10-dimensional space. The data has 10 numbers, but the model has only 3 free parameters. We say 3 degrees of freedom. So it lives in a subspace of 3 dimensions. We can construct the M matrix. Here's a slicker way to construct the matrix. M is equal to t dot hat 2 by minus 1 to 0. Oh, that didn't work. Oh, I got the wrong bracket. Yeah, and it created the same thing. So this is an even slightly slicker way to generate a model, a polynomial. So this is t to the power 0, t to the power 1, and t to the power 2. All right, now let's construct our beta. That should be m. We can just do m backslash d, that would work. But let's use the explicit formula, m prime star m slash m prime star d. And this is our 3 values of beta for this model. Again, just to convince you that m backslash d also produces the least squares, or the normal solution to the normal equation. I could do it a second time, we get the same answer. All right, so the other beta, which has 3 parameters, a, b, and c, and its values are minus 0.1309, minus 0.3676, and 2.8452. And let's plot this model on top of the other ones. So f is equal to m star beta. Plot, and the last one I plotted red, this one I will plot in black. Oh, I should put the circles, well, maybe not. That's pretty good actually. All right, so there's our 3 models. I can stretch a little bit. So the curved one seems to do a better job, right? We have a point below, a couple of points above, 1 below, a few, oh sorry, I guess 1, 2, 3 below, 2 above, and 2 below. So it seems the points are better distributed. To know which one is the better fit, we would have to use probability theory to assign a statistical model and then make some conclusions based on how probable the different models are, and that will come later in the course. But we can also compute the errors and see which one has the biggest error. So let's go to a script. So example 4.m. Oops. Try it out. Clear all CLF. Example 4. All right, so let's look at what we've computed. So I have M1. Whoops. M1. That's the model, the intercept, and the time dependence in the model. Beta 1 beta 1, the slope and the intercept, F1, the best fit model, and E1, the vector of residuals. So let's plot all these. Plot T, E1, circle black with the line. And then hold on, plot T, E2 with the line squares in red. So this is the residuals. Let me put make the font size bigger. Set GCA font size. So these are our two error vectors, the components. Remember, they live in a 10-dimensional space. And the red one, see the 0 line is over here in the middle. So in general, the red one is mostly closer to the 0 line almost everywhere. Not everywhere, but almost everywhere. To get a quantitative estimate, we can calculate the sum of the squares of the values of E. So if we compute that, E, so that's the equivalent to computing the length of E. So E1 dotted with itself is going to be the sum of the squares. And now we'll do it for E2. And it's smaller about by a factor of 2. Right, this one is 18 and this one is around 9. So the second model fits much better. Of course, it has an extra free parameter, so it's able to fit the data better. Let's look at what the projection matrices look like. So P1 should be a 10 by 10 matrix. And it is because the data lives in a 10-dimensional space. But in fact, there were not, if I was to look at the columns here, there are only 2 independent columns. So it looks like we have a 10 by 10, but the columns are all parallel to each other. They all live on the same plane. All right, so now I'm going to convince you that the projection formulas that we derived with the normal equations are the same ones we would get if we did a least squares problem, where we minimize the sum of the squares of the differences between the model and the data. So I'm going to demonstrate this for a special case, the one we just worked with, where we fit the straight line through the data. So the data, remember, D is a vector of 10 numbers, D1 all the way up to D10. T is a vector of times, T1 up to T10. The fitted model F is of this form, A T1 plus B, A T2 plus B, all the way up to A T10 plus B. And the error, E, is equal to D1 minus A T1 plus B, D2 minus A T2 plus B, all the way down to D10 minus A T10 plus B. And so for the least squares, what we want to minimize is the sum of the squares of the components of E. So let's give this a name. I'll call it chi squared is equal to the sum for I equals 1 to 10 of E sub I, which is equal to E1 squared plus E2 squared plus dot 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 plus E10 squared. And then if I sub in my formula, the expressions I have for each E, I'll get D1 minus AT1 plus B squared plus D2 minus AT2 plus B squared plus all the way up to the last one, D10 minus AT10 plus B squared. And if we're going to be at the minimum, then that means the derivative of chi squared with respect to A should be 0, right? Because if you're at the minimum, the slopes are 0, right? Because they're decreasing on one side of the minimum and increasing on the other. So that means that the derivative of chi squared with respect to A is 0 And the same thing for b, the derivative with respect to b is also 0. Those are necessary conditions to be at a maximum. At a maximum or a minimum. In this case I want a minimum. So let's take that derivative, d by dA chi squared is equal to, and so for the first one I get 2 d1 minus at1 plus b times the derivative of the inside, which is just minus a. No, sorry, it's just minus t1. My brain slip up here. Minus t1. And then the next one, plus 2 times d2 minus at2 plus b times minus t2 plus, and all the way to the last one, d10 minus at10 plus b 2, and then derivative of the inside with respect to a is minus t10. Right, so this quantity here, this is just E1, this is just E2, and this is E10. So this is the same thing as 2 times E1 T1 plus E2 T2 plus all the way up to E10 T10 with a minus, right? They all have a minus, minus and a 2, minus and a 2. Another condition I have for to be at the minimum is that the derivative with respect to b is also 0. So let's do that one. D chi squared db is equal to 2, and this time I already know this is E1. E1 times the derivative inside with respect to b is just minus 1, so I'll put a minus. The derivative of the second one will be 2E2 minus the derivative of the inside, oh up here, the derivative of the inside with respect to b is just minus 1. And I keep going all the way up to the end. Minus 2E10. My condition to be at a minimum is that this should be equal to 0, and this should be equal to 0. So you can see now that what I get is the 2's, the minus 2 I could cancel out. So I have E1, E2, all the way up to E10, dotted with T1, T2 up to T10, T1, T2, all the way up to T10. Has to be equal to 0, so that's from the first equation. From the second one, what I get is that minus 2 again, I could cancel it. I have E1, E2, all the way up to E10. And that's just the sum of the errors, which is equivalent to dotting this with the vector of 1's. And, computer died. And so you see we get back the same equation, that E dotted with the first column of the design matrix M, right, was T1, T2, T10. And so I know that the error vector dotted with T1 through T10 is 0, and the other one is that the 1's, the E dotted with the 1's is all 0. But we can try to get it in an explicit formula. So if we didn't recognize this, we can keep going to an explicit formula. All right, so this demonstrates that we have the same conditions that we derived through the projection by requiring orthogonality. But let's go and get an explicit formula for A and B. So if we collect all the terms that multiply A in after having canceled out the minus 2. So what multiplies A? Well, maybe I'll keep everything. So we have 2 and a minus sign, and we have another minus sign on the inside, which makes it a plus. And on the inside we have a T1 times T1, which is a T1 squared. So T1 squared. From the second term we have the same thing, but it's a T2 squared. plus, and we can keep going all the way up to the last one, t10 squared. And that all those terms always multiply a. And then we'll collect all the terms that multiply b. So plus 2. So what multiplies b? We have a minus 2 times minus t1. So minus minus makes it a plus, and then we have t1 plus t2 plus all the way up to t10. That multiplies b. And that, no, yes, is equal to everything that multiplies neither a nor b, which is, if we bring it over on the other side, it's going to be t1 times d1 plus t2 times d2, everything multiplied by 2. 2 t1 d1 plus t2 d2 plus all the way up to t10 d10. And now we'll do the same thing for the second equation, the one involving the partial derivative with respect to b. And this time we'll have a minus 2. Well, let's write it out. So minus 2 times e1. So it's minus 2 times d1. That's on the right hand side. For a is plus 2a times t1. So 2 times t1 plus t2 plus all the way up to t10 times a plus 2 times, and for b we have minus minus 2. So minus 2 times minus 1 is just 2. So that's just 1 plus 1 plus 1. 1 plus 1 plus 1 10 times. So that's just equal to 10. And then on the right hand side we have 2d1 plus 2d2, and then we bring it to the other side, makes it a minus. Oh, and there's already a minus out here, so that'll make it a plus. So it'll be plus 2 times d1, 2 times d1 plus d2 plus dot 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 plus d10. Alright, so these two equations, two unknowns, are going to be the following. The 2's cancel, and so I have the sum of the t's squared times a plus the sum, the 2's cancel, remember, the sum of the t's times b is equal to the sum of t times d. And the other formula, the bottom one, the sum of t sub I times a plus the 2 cancels from the second equation, the sum of the 1, so this is just going to be 10. And the sum of the data. And we can rewrite it in matrix form to compare with the other formula that we had before. So this becomes Alright, so we'd like to show that this formula is the same one that we had before. So what were the previous equations? Remember, they were just m primed m times AB is equal to M prime D. This was the normal equations. So let's compute M primed M. M primed is going to be T1, T2, up to T10, 1, 1, 10 times, T1, T2, up to T10, 1, 1, 10 times, AB equals T1, T2, T10, 1, 1, 1, D1, D2, D10. And now we can multiply this out. So this multiplied by this is going to be T1 squared plus T2 squared all the way up to T10 squared. So the first element of my 2 by 2 matrix will be the sum of the T sub I squared. So the first one matches. Then this multiplied by this will be T1 plus T2 up to T10. So this is going to be the sum from I equals 1 to 10 T sub I. It matches this. The lower corner is this dotted with this is going to be the sum of the T's again. 10, so far so good. This matches this also. And the last one, the vector of 1s dotted with the vector of 1 is going to be 1 times 1 plus 1 times 1. So we'll get a 10 again. So all the coefficients match up. We just have to make sure the right hand side also matches up. So if I do T1 times D1 plus T2 times D2 all the way to T10 times D10, I get the same thing. Ti di I equals 1 to 10. And then for the other one I get D1 plus D2 all the way to D10. And so this formula is the same as this one, so we get the same solution. All right, so I hope you agree that the method with calculus is a little bit harder than the projection method. If you're willing to learn a little bit of the geometry, the case using projection is easier. The calculus one is still useful to know, because if we would have had a problem where the parameters appeared non-linearly in the model, then it wouldn't have been true that the model is spanned by a plane or a hyperplane, a vector space. And in that case, we'd have to use some other methods to find the solution. So we'd have to use calculus to find the derivatives and set them to 0. The problem is we would end up with a set of equation which is not a linear system of equations, and that will be harder to solve. All right, so that's it for today.